Hello students, welcome to another tutorial on fluids in motion. In this video, we're going to introduce the concepts to do with the Bernoullis equation. So we're going to start by looking at Bernoullis principle, what it states. And then after that, we're going to look at the equation that he came up with and how to use it. So we're going to use the Bernoullis equation to work out the question I left you guys with in the previous video. So I hope you guys had time to go through this question. So if you haven't, you can read through the question, you can pause the video, just read through it, understand the question and try to work it out. And if you have done that, let's look at what Bernoulli came up with. So let's start by looking at the principle itself. Now, what does it state? See, Bernoullis is a concept of conservation of energy. But one key thing that he came up with, one key thing that was concluded here, this is going to be called, or this is called the Bernoullis Principle. Now, what does it state? Well, in simple terms, the conclusion is this. Where velocity is high, where the velocity of a fluid is high, the pressure is going to be low. And where the velocity is low, the pressure is going to be high. Well, what does that mean? If you have a fluid that is flowing in some tube, let's say this is the first scenario. Let me pick 2 points here. So let me pick 2 points. Let's say this is point A, and this side, this is point B. Now, if you have a fluid that is flowing inside here, so if we have a fluid that is flowing inside this tube, and then we have at point A and at point B, one thing that you guys will agree with me is that we expect that the velocity at point B is going to be greater. So the velocity is going to be high. And then at A, the velocity V is going to be relatively low. Now, what Bernoulli concluded is that if the velocity at B is high, then what we expect is that the pressure at the same point is going to be low. So pressure here is going to be low. And if at A the velocity is low, then what we expect is that pressure is going to be high. Now, if you try to think about it, this is where you might start to wonder, wait, you expect that with the increase in velocity, then the force here is supposed to be greater, implying that the pressure at this particular point is supposed to go up, or the pressure is supposed to be greater at point B as compared to point A where the fluid is slow. Well, if that's the case, think about it like this. If point B is at high pressure and point A is at low pressure, but then how possible is it that the fluid is going to flow in this direction? Because what we know is that fluids flow in one way. Fluids will flow from high pressure to low pressure. So this is literally how fluids will flow. So if at point A, you have low velocity, Bernoullis says you're supposed to have high pressure there. And this actually makes sense with our statement here. We expect that fluids are going to flow from high pressure going towards low pressure. But if we end up with a situation where at B, we have high velocity and then we also have high pressure, then this is going to slow down the flow of the fluid, meaning that the motion of the fluid going forward is going to be hindered. So it only makes sense that point B is going to be at low pressure to enable the fluid to move in that particular direction. Okay, so that is a simple explanation that you guys can look at to help you understand why Bernoullis principle actually holds in this case. Above all, one key thing that you have to get true, yes, at point B you might have higher pressure, but that is only if you were to put an obstacle in the path at that particular point, yes, an obstacle there is going to experience a greater pressure as compared to point A. But in terms of inside the tube, without that obstacle, point B is going to be at lower pressure as compared to point A. So all you have to remember is if velocity is high, pressure will be low. If velocity is low, pressure will be high. That is what Bernoullis principle is all about. Now, this of course will be true whether you have something that is linear like that, or something where one section is going to be elevated. Like, let's say if you had something like, let's say like that, and then it goes up. The Bernoullis principle will hold regardless of the scenario. So you can say this is one point and that is the other point. It will still hold regardless. Okay. Now, let's start looking at what Bernoullis equation is all about. See, here we're saying Bernoullis is all about the conservation of energy. Not really energy. We're really just looking at the work done. So in the end, it's going to simplify to just be something to do with energy. So now, if you picked 2 points in a fluid that is flowing, what you're going to end up with is, so we can, literally any system is going to work. So I can use something like this. So where this side, I can even elevate it a little bit. Okay, so let's work with something like this. So the idea here is very simple. So if you have a section of a fluid that has to flow in one direction, let's say we have flow in that direction, and then you have another chunk this side that gets to be pushed. So of course, this side, what we are experiencing is a push in that direction. Then in simple terms, or if we just look at the equation, we can derive this equation, but then we have to look at so many factors. We can do that. But let's just look at how we can actually apply the equation. So in the end, we're going to end up with the pressure at 1. So if this is at the first point, this is at the second point. So what we have is P1 plus rho Gy1 plus half rho V1 squared will be equal to, this is going to be P2 plus rho Gy2 plus half rho V2 squared. Now, what do these terms mean? So first and foremost, we want to just know the Bernoullis equation. So this is the term, the equation that we're calling the Bernoullis equation. And then after this, the next step is going to be deriving this equation to see exactly how it comes up. So the first part, the most important thing for you guys at this level, is to know how to use this. It's rare that you find a question in the exam where you are asked to derive the Bernoullis equation. So that is why I'm starting with just showing you guys what the equation is and also how to use the equation. The next part will be showing you how to derive the equation. So you're free to stick around at that part. It's interesting, yeah. I think it helps you understand how to use it when you know where it comes from. But you can still get everything just by looking at this brief description. Trust me, you lose nothing still. Okay, now you see this first part here, the P1, this is the work per unit volume done by the fluid. This is basically just the pressure at point 1, but I'm saying it's going to be the work per unit volume done by the fluid. And then next up, this quantity that we have here, this comes from the potential energy. So if you have 2 points, so this is 1 and that is 2. This where you have Y1, this is basically the potential energy at 1. So I'm going to draw one line here. This is where Y1 is going to be measured. So Y1 will always be measured from the central point of the tube this side. So it has to be on the central point. So it's basically just an average. Okay, now next up, the third term on the left-hand side, it's a kinetic energy term. So it's the kinetic energy per unit volume. So this is the potential energy per unit volume, and then this is the kinetic energy per unit volume. This is all at 1. And then when you go to the other side, the right-hand side, this is the work done per unit volume, and then this is the potential energy per unit volume, and lastly, that is the kinetic energy per unit volume. Now, depending on the type of system that you're dealing with, for this diagram that I've drawn, what you observe is at 1, let's take this to be the rest position, meaning y is 0. If this is the case, you guys should be able to observe that this term quickly becomes 0. And then at point 2, what we have is this is actually elevated. And since it is elevated, we see that there is actually a quantity y2. So we expect every term there to remain. So depending on what they want us to find, if they want us to find the pressure difference, we just subtract P1 minus P2, move everything the other side, we'll easily get the pressure difference. If they want us to find any quantity here, just look at what you're given, evaluate everything. So always start at point 1, do we have pressure? If we do, this term remains. Do we have, is it at a height at point 1? If that is a reference point, then the height is 0, the potential term disappears. And then next up, is the fluid flowing at point 1? Most likely it will, meaning that you're going to have this term. But if it is not, this term will disappear. Okay, then you go to the right side. The right side, that is at point 2. It's the same questions. Do you have pressure at point 2? If you do, the P2 term will remain. And the next thing is, do you have some height there? Is there potential energy there? If there is, then the term here will remain. And lastly, is the fluid flowing at point 2? If it is, then you're going to have that kinetic term, which will also remain. Okay, now before we actually look at how this equation is derived, let's quickly go and try to work out the question that I started by showing you guys. Let's see how we can actually use this equation to work out that particular question. Okay, so ideally, the equation is the same. So what we have is P1 plus P plus, this is the density, GH plus half rho V1 squared equal to P2 plus rho GH plus half. Then we have rho V2 squared. So here I'm just using rho because the densities are the same. It's the same fluid. So I'm just using rho without really saying rho 1 and so on. Of course, in terms of the height, this we can say this is height 1, this is height 2. This is where I had y in the original formula. But then if we go back to the question, if you guys can look at the question, so I hope you have the question somewhere. You can quickly get it. If you don't have it, you can just try to get where it is. Okay, so here we're talking about a person who inhales air. So let's quickly just go through so that you guys will have it. So we're saying when a person inhales air, air moves down the bronchus at 15 centimeters per second. The average flow speed of the air doubles through the constriction of the bronchus. Okay, assuming incompressible flow, determine the pressure drop in the constriction. So they want the pressure drop. So here we have to calculate the pressure difference. So that is where we're going with this. So once the pressure drop, and the pressure drop is going to be the pressure difference. And what is that? So we have to evaluate P1 minus P2. Okay, so this is where we are looking at. Now, the key thing that I want you guys to keep in mind is when you're looking at these questions, if you see there is no mention in the question about viscosity, then most likely the Bernoulli equation can work. But if the question gives you the viscosity, then you have to start thinking of, wait, maybe I have to use the Bernoulli equation. So try the Bernoulli, not the Bernoulli equation. You have to use the Bernoullis equation if there is viscosity in the question. But then, of course, we'll see exactly what that equation is and how to use it later. Okay, so let's quickly come back to this. So this is what we want to evaluate. So I'm just grouping P1 and P2. So P1 is already on the left side, P2 is the other side. So if I move it, this is what I have. Now, H1, so if we take this to be on a level surface, let's say this is happening on a horizontal, on the same point, meaning H1 is 0 and H2 is 0, meaning this term becomes 0 on both sides. What will remain with is only the kinetic term on each side. So I can move this kinetic term to the other side, meaning that what I now have is half rho V2 squared minus half rho V1 squared. So this is now what I have. Again, the density is the same, and I can factor out half rho. Now what I have is V2 squared minus V1 squared. So from here, I think we have everything that we need. So we can now start performing our substitution. Now, look at one interesting thing. Look at what they're saying. The average flow speed of the air doubles through a constriction in the bronchus. So when a person inhales, so this is what we have, but then it doubles. So in other words, when it doubles, what you have to look at is V2 is equal to double V1. So when I use this, now what I have is P1 minus P2 is equals to half rho. So where there's V2 here, I can put V2 V1 squared minus V1. And this becomes half rho. This becomes 4 V1 squared minus V1 squared. And then this can be simplified. This will now be half rho 3 V1 squared. Okay, so V1 is the initial velocity, which is given in the question. So initially that V1 is given as 15 centimeters per second. So we can convert this to meters. So we know in every meter we have 100 centimeters. So all we have to do is in every meter, that 100 centimeters, this is going to perform the conversion for us. So this will end up as 0.15 meters per second. So when we substitute, we know the density here, the density is given as well. So the density we're using, let's look at our question. Okay, so the question doesn't give us what the density is, but we know what we have to use. You guys can just look it up. So the density that we're going to use here is 1.225. So when we substitute these values, what we now have is the drop in pressure, P1 minus P2. This will be equal to, so what we have is half multiplying the density of air, 1.225, multiplying 3, multiplying 0.15, the velocity, but this has to be squared. So from here, when you evaluate the right-hand side, what you get is 0.0413437.5 pascals. So you can write this in scientific notation. So this becomes 4.13 by 10 to the power negative. You move this 2 places, -2 pascals. So this becomes the pressure drop. So I can even write change in P. So this is the value that they were asking, they wanted us to find. Okay, so yeah, I hope you guys were able to follow through. I hope you guys were able to get this question. Yeah, I hope you're able to get it right. So I think I'll leave the part for deriving the Bernoulli equation for a different video. I think I'm going to make a separate video for that one so that I avoid making this video longer than it has to be. But then I can leave it to you guys. If you guys want to see how to derive the Bernoulli equation, you can go right ahead and comment in the chat, in the comment section. I'll look at that, and if you guys are requesting for it, we're going to make that derivation video so that you guys know exactly where the Bernoulli equation comes from. Okay, so one key thing to take from this, the Bernoulli equation is the conservation of energy that we have to look at. So it's basically just the work done that we all have to just conserve. So it's a statement of conservation of energy. The energy before is equal to the energy after. For this question we worked out, it was happening at a level surface. We took it that it's happening at a level surface, implying that the potential term is not there. But you find that there will be other questions where you have to keep the potential term as well, meaning that the height will not cancel out like the way it did here and there. So most likely it might cancel one place, but it might not cancel the other side as well. So you guys have to just keep an open mind to that. We'll look at more questions where the Bernoulli equation has to be used. But otherwise, in the meantime, the next concept that we're going to look at is going to be the Bernoullis equation, unless if you guys request that we make the derivation for the Bernoullis. But otherwise, the next video we're going to look at is going to be the Bernoullis equation. We're going to look at what it is and also how to use it. So we'll define every term in the equation, then we're going to see how we can use that equation to work out this particular question. So again, like I said, whenever a question you see mention of the viscosity, then in your mind you should quickly start thinking of, can I use the Bernoullis equation? Don't rush to use the Bernoullis equation where you're seeing viscosity. Try to use the Bernoullis equation first before you move there. Okay. All right, you guys. So we're going to end the video here. I hope you guys found this video helpful. If you still have any problems, feel free to join one of my live sessions. So I am going to have the next live session on 28th of October 2021, where I'm going to be presenting these same questions that I've just presented in this video. So if you want to attend that one, and it's going to be more instructive and longer than this. So if you want to attend that one, maybe you have a question that you still have in your mind after watching this video, just leave a comment in the chat section. I'll leave you guys a link to that meeting. I have one meeting at 17 hours. You're welcome to join that. Okay. All right, you guys, thank you very much for your attention. We're going to end the video here. This was your tutor. We'll see you next time.